Hey guys, and so welcome to our first lecture on relativity. So basically, I want to take this lecture to kind of walk through the material and get a general understanding of exactly what I'm going to be discussing, and kind of also motivate why relativity is so important nowadays if you want to understand modern physics and general concepts in STEM today. The breakdown for today will be I'll kind of go through what is relativity, the history of relativity, a brief recap, and then talk through some applications and then the course outline. So I'll kind of start off first with why relativity. And I have a pretty simple answer to this, but anyone who is looking to understand modern physics should have a one-on-one understanding of relativity. The reason why is because science as we know it, as we're starting to reach deeper, more fundamental models of nature, we have to take into account relativistic effects and also understand ways to describe gravitational effects and quantum mechanics hand in hand. So there's a theory called quantum gravity, and there's a whole spiel on like exactly how we use that to understand various mechanisms at the astronomical level as well as at the microscopic level. And so, that's a pretty soft motivation, but in general, if you want to, there's multiple applications that I'll walk through a little bit later on, but this is kind of a general thing to understand if you wanted to get into physics, especially in grad school and things like this. So in terms of the history, um, I want to paint a summary picture, and then I will say that I'll kind of get to explain a little bit more of these concepts and flesh out some of the misconceptions that happen in history and things like that as the lectures continue. But you can also find lots of material on this, and I actually encourage you to go, research on the web and Google different descriptions and different ways that people have presented the history of relativity. Just because you learn a little bit more about some of the fundamental like paradoxes and things that physicists were confused about back in the day, and then you'll also learn more about Einstein and his background, which I think is actually it's funny, but it's also interesting at the same time. So I actually highly encourage you to go out and do that. But I'll just kind of give you a quick snapshot today. So the whole story starts with the principles of how physicists described light and electricity, magnetism, and light. There we go. And so, the way to kind of start this off, let's start in the 1800s. Through the 1900s, there's a lot of development on battery technology, electromagnetic theory, the wave theory of light, and later in the late 1800s, we also had the Michelson and Morley experiment, also known as the discovery of research era of the ether, the luminiferous ether. And then in 1905, Einstein. This is there's a large history on Einstein. Like I said, I highly encourage that you go to look up a deeper explanation of the story. But I'm just trying to give you more of a snapshot, high level view of exactly what the story of relativity was. And so in 1905, we had Einstein's special theory. And so the reason that Einstein had a special theory was that there was this idea or concept to him that he learned in his group, that if you have more than one way of arriving at the same result, then there should be one uniform way to describe this result. And so this kind of came out of Maxwell's equation. So if you take the concept where if you have a moving magnet and a stationary coil and sort of have an electromotive force induce a current in the coil, or if you were to move the coil and you arrive at the same description, then you shouldn't really care about how you arrange your equations to account for whether or not the coil is moving or the magnet is moving. And so basically, this kind of put him into this space to describe kind of in a once and for all way how electromagnetic waves interact with the world, and try to come up with a way to mathematically describe this. He also contributed to our wave particle duality picture of light that we have here. And so, this was kind of a very groundbreaking thing because, the way that we understood electromagnetic waves is that they were a wave. So, we anticipated them to kind of had this, this transverse undulation that kind of created these different forces in fundamental particles and atoms. But for some reason, there are experiments in history that demonstrate that the way that we can see certain results by trying to control light, the results don't necessarily line up with necessarily one or the other. It's more of both. And then in 1915, later on, we had Einstein's general theory of relativity. And so this was just kind of an extension of Einstein's special theory of relativity, and you see that going into many various applications, especially in terms of studying gravitational fields, stars, astronomy, and things like that. So to kind of talk a little bit about the applications of the special theory of relativity, these are just some three big ones that I had. You have GPS navigation and also trying to do like satellite communication. So if you work in NASA, or you're doing something that has to do with communicating at a large distance, and typically you might be communicating via light or something like this. You have to take these relativistic effects into account so that you can make sure that when you're reading back the information, it's reading back the way it should. Excuse me. And then you also have astronomy and black holes. So Einstein's theory of relativity was able to predict the existence of black holes. And so if you're interested in studying, things in space, which I'll say I'm personally not that well versed in, then, this is another application of it. And something that I would say that I'm a little bit more interested in would be the elementary particle physics. The elementary particle physics, because somebody like me who's actually interested in materials physics and more of the fundamental building blocks of matter and the way that matter interacts with light and various forces that we understand in nature. This is actually something that's actually really important. When you go to study quantum mechanics, you learn the basic principles of the Schrodinger equation, ways that you can describe the dynamics of a wave function. But when you start to account for relativistic effects and you want to understand relativistic quantum mechanics, that puts you into quantum field theory, and then quantum field theory helps you to understand is a more effective theory in terms of how to describe the dynamics of these various particles, and it also gives rise to predicting the existence of these particles. So I think that it's actually pretty interesting, but relativity kind of pours into all these different things. And so lastly, I kind of close out this first video by the series outline. I will say that I am following Griffith's Introduction to Electrodynamics, Chapter 12. If you're studying for the physics GRE, this is a pretty common book to refer to. You also have classical dynamics of particles and systems, and so that's something that you can also refer to as well. But I actually like Griffith's writing style. I'll also be referring to him for my quantum mechanics lectures, but I think that he has a very great and effective way to communicate very difficult concepts in relativity, and so I think that it's really helpful. But so in terms of the outline, I have 5 different topics that I want to cover, and I'll also I'll have videos coming after this. Closing out the luminiferous ether. So what I'm going to do in this lecture is I'm going to discuss exactly what Michelson and Morley were trying to do and what exactly came about as a result and what led to Einstein's special theory of relativity. And we'll talk about Einstein's fix of the relative velocity equation, the Galilean-Newton relative velocity equation. Then we'll discuss Lorentz transformations, proper time and velocity, and relativistic energy and momentum. And so, as we step through each of these topics, I will go through exercises, and I hope that you guys will be able to follow along. And if I will try my best to really go through rigorously and describe step by step why each line of math is the way that it is, and exactly what assumptions are made, and really talk through exactly how the solutions are meant to work. And so the problems I'll be working through will be from Griffith's textbook, and I will have more exercises than I will actually talk through. I'm listed on my GitHub. And so I'll have that link in the video here. And so thanks for listening. See you in the next video.